The problems that we are going to do now are based on determination of displacements. So determination of displacement is actually straightforward, and we will do one problem in Cartesian coordinate system and one problem in cylindrical polar coordinate system. And when we do the problem in the cylindrical polar coordinate system, we will use the other part of the Michel table. But let's concentrate on how we go about doing this. So we have already seen we determine phi, which satisfies this for the case without body forces. With body forces, it's slightly different. So this we find, then we find the stresses, and then we'll use the constitutive equations to find the strains, and then we'll integrate the strains to find the displacements. So this is the path that we are going to take. We are now going to concentrate on this part and this part as well. So what relations you use to go from the stress to the strain will depend on whether you have a plane strain problem or a plane stress problem. Okay, and this, in at least in Cartesian coordinate, is best taught by an example. So let us look at a problem where the problem is, I think, like this. So I have a cantilever beam which is fixed at this edge. This length is A, this is 2B, and you have a load applied like this. The coordinate system is here, x1, this is x2. So this is your problem. This is the problem that you need to solve, and let's assume that part of the problem is already solved. So I already have the stresses. I have calculated the Airy stress function. I have the stresses given to me, and then I now want to find the strains and the displacements. And now I have to pay attention to the fact that this is a plane stress problem, which means that the thickness of this beam in the out of plane direction is small. I'm going to use the plane stress constitutive equations, which give me the strains in terms of the stresses by these three equations. Okay, so these are equations you should verify. Go back to your isotropic linear elastic constitutive equations for plane stress and verify that these are indeed the constitutive equations that you should use in this context. So once you have these constitutive equations and you have the stresses, it's easy to find the strains. So you just plug them in, plug these stresses in to the constitutive equation, you get the strains. Once you get the strains, and we have done this problem before when we did the chapter on strains. So epsilon 1 is del u1 del x1, epsilon 2 is del u2 del x2, and epsilon 1 is half u1 comma 2 plus u2 comma 1. So we are first going to use this. So we are going to integrate this with respect to x1. So we'll get x1 square by 2, and then a function of x2. We will integrate this with respect to x2. We will get x2 square here and the function of x1. Then we are going to put both the expressions into 1, 2 and try to determine the functions. This is what we had done before also, and we also had a few problems in your quizzes. So it's straightforward. Epsilon 1 is this. So u1 would be integrate with respect to x1. You get this and an unknown function of x2. Similarly, u2 is this unknown function of x1, and now you use the fact that epsilon 1 is, for epsilon 1 you know epsilon 1 is this, and now you carry out u1 comma 2 and u2 comma 1. You have an expression for u1, you have an expression for u2. take the derivatives, and this is what you will get. So this here, g is a function of x1 only, f is a function of x2 only, and this is completely split up, which means that I can now break it up into two parts, one which is a function completely of x1 and the other which is completely a function of x2, and both of these have to be equal to a constant, undetermined constant. So I have two differential equations now, one in g and x1 and f x2, and I need to solve these two differential equations in order to get the g and x, which is pretty easy in this case, and these are the displacements that we get. Now these displacements contain these terms. Okay, what are these terms? These terms are quite easy to understand from a physical point of view. Why do we have these constants here? So the first constant, a here, is a constant. So it doesn't depend on x1, x2, which means that it's a rigid body displacement in the one direction, similar to b, which is a rigid body displacement in the two direction. What about this? Now, if I have a coordinate system x1, x2, and I have a point here, let's say this is r, this is theta, and this point is x1, x2, let's say, and then I give it a small rotation whereby the point moves here. Okay, so let this angle be phi, and phi is small. Then this new coordinate system, the new coordinates of the point x1 prime is r cos theta plus phi, and x2 prime is r sine theta plus phi. Here r sine theta plus phi is r sine theta cos phi plus r cos theta sine phi, but the original coordinates was this was x2, this was x1, so this becomes x2 cos phi plus x1 sine phi. Now if phi is small, this is 1 and this is phi, so x2 prime minus x2 will be almost equal to x1 phi. So this is your u2, this is u2, and this u2 is some constant c times phi 1. So this term actually represents, and if you do this, you will find that x1 prime minus x1 will be almost equal to minus c minus phi x2. Okay, so these two terms represent a rigid body rotation about the origin by a small angle c. So these first two terms are rigid body translations in the x and y direction, and this second term here is a rigid body rotation about the origin, about the three axes, a rigid body rotation about the origin and about the three axes, that you can arbitrarily give so that these u1s and u2s still satisfy the strain equations. So these rigid body terms will not give rise to any strain. So if you now calculate epsilon 1 1, you will see that del u1 del x1 will this will cancel out. This will obviously cancel out, and this will also differentiate out because this contains x2. Similarly, if you do del u2 del x2, this will go to 0, and this will of course go to 0. So these terms have no bearing on the strains. They have no bearing on the strains. The strains come from this, but the displacements are arbitrary up to uh, arbitrary translation in the x direction, arbitrary translation in the y direction, and an arbitrary rotation, arbitrarily small rotation about the origin. Okay, so now depending on the problem, like we have the problem here, depending on the problem, these rotations and translations will be restricted by conditions on del vu, which in this case is this. This is your del vu, and the built-in edge there will will prevent the rigid body rotation and translation of this cantilever beam. Okay, so now the question is, let me erase this. What kind of boundary conditions do we use? So I have to determine A, B, C. There are different kinds of boundary conditions that we can use. We of course can use that everywhere in at x1 equal to a, u1 and u2 are equal to 0. That's a boundary condition that we can use, but that's too strong a boundary condition. We have only three constants to determine, so we will not be able to determine three constants from this very strong boundary condition. On the other hand, we can resort to different kinds of weaker boundary conditions. For example, we say, okay, I don't want it everywhere to be 0 on the right edge, but I just want it to be 0 at the center and the slopes to be also 0 at the center, something that I borrow from my knowledge of strength of materials of cantilever beams. So if we do this, we will indeed be able to solve the equations, and these are the constants that we are going to get. So we can of course use different other kinds of boundary condition, weaker boundary conditions of different types. But then we know from Saint Venant's principle that differences in boundary condition will lead to different sets of A, B, and C constants. But those effects of these differences are going to persist only very close to the boundary and far away from the boundary by the Saint Venant's principle. It's not going to really matter. So